Okay, hello everyone again. So let's start for today. And in the last class, we had actually completed the topic of DC amplifier. Okay, and we saw a special kind of DC amplifier that was chopper based. Okay, chopper stabilized DC amplifiers. So okay, we had seen that thing. Okay, so let's start a new topic. On OPAMP, okay, or operational amplifier. So we are all aware of this, okay, right from the first year, I think, when you started studying basic electronics. uh, you studied this topic in that same subject. Okay, OPAMP is basically uh, operational amplifier. And why it is called operational amplifier? Because it can perform a variety of operation. Okay, it can perform addition, subtraction, multiplication, even log, exponent, and many other functions. Okay, so and because of this fact, it's called operational amplifier, right? So basically, it's a difference amplifier or differential amplifier having a very high gain, very high value of gain. Okay, and the input impedance is also very high, and the output impedance is low. Okay, and remember the four important parameters that were there to define a good amplifier were input impedance, then output impedance, okay, then current gain and voltage gain. Okay, so these were the four parameters that were important from any amplifier point of view. And ideally we want to have infinite value of you know input impedance and a zero output impedance, and we want to have a high value of gain, okay, just a minute. Okay, so and this OPAMP is very popular, is a very popular amplifier, and is being used in amplifiers. It is used to make oscillators. It is used in filters and many types of instrumentation circuits where we need to uh, measure and amplify very small magnitude signals. Okay, so it's basically a very popular amplifier, and it comes in a very popular IC numbered as IC, if you remember from your lab, basic electronics lab. IC 741 was the IC that you used for doing the things experiments with OPAMP. Okay, this particular IC. Okay, now we can use basically input. Basically, OPAMP will be having two input lines, and we generally denote them with plus and minus. Plus means non-inverting input, minus means inverting. Okay, so when we ground one of them and apply signal to only one input, it's called a single ended input usage. Okay, and remember, look at here that if the signal is applied at the positive non-inverting terminal, okay, the amplification is there is amplification, means this signal is amplified version of this input signal, but the phase difference is also maintained. There is no phase difference between them, there is no phase shift. Okay, so in this case the phase shift is 0. Okay, it will be 180 degree, the phase shift will be 180 degree. Okay, the amplification will be there, and the phase shift will be 180 degree, that is the output signal will be out of phase with respect to input signal when you apply signal to the non inverting terminal. Okay, so this is the meaning of this plus and minus. So it depends on the type of usage whether you want your output signal to be out of phase with respect to input signal or not. Okay, again we can also give signals to both of the input terminals, then in that case it will be called as a double-ended differential input usage of the op-amp. Okay, look at here, for example, V1 is given here at plus terminal, V2 is given here. Okay, and the property is op-amp's property is such that it will amplify the difference of the input signals. Okay, and the difference is Vd, so Vd will be equal to V1 minus V2. Okay, and V1 or V2 will not be amplified individually, but rather the difference, that is V1 minus V2, that particular value will be amplified and will come at the output terminal. Okay, so this is one important thing, just take care of this. Okay, then let us see some of the characteristic of ideal op-amp. Because practically the practical op-amps that are available in the form of ICs, their characteristics are we can say that their characteristics are close to ideal op-amp characteristic. Okay, so let's start with the ideal let's start with this ideal op-amp characteristic, and you will find that when you use practical op-amp IC, you will find that that gives you quite an impressive amount of performance, quite an impressive value of performance. Okay, so it means that the practical ICs of op-amp will be having a high value of bandwidth, will give a high value of gain, and many other things which are similar or which are close to ideal op-amps, and which is generally hard to find in other kinds of amplifiers. Okay, so when coming to ideal op-amp characteristic, the first and foremost thing is that op-amp is basically designed to sense the difference of input signals. Okay, remember, it will amplify the difference of input signals that will appear at the output terminal. Okay, and now the input impedance should be infinite. Okay, the input impedance infinite for an ideal, it's desirable for any ideal amplifier. Okay, so input impedance is infinite. So it means that if the input impedance is infinite, it is not drawing any input current. So wherever there is infinite amount of resistance, the current would be zero simply. So it means that the input terminals will not be drawing any current. So I input would be 0 ampere, simple. Okay, now the output impedance is supposed to be 0, that is output impedance is 0 for the case of ideal op-amp. And when you look at the internal diagram of op-amp, okay, you will find that there is a dependent source connected at the output terminal. Okay, and with this assumption that output impedance is 0, basically it means that the output terminal will act as an ideal voltage source, that is output terminal will act as an ideal voltage source having a value of A naught into V2 minus V1. Okay, where A naught is the open loop voltage gain, okay, and V2 minus V1 is the difference of input signals, and the value of open loop voltage gain is actually infinite. Okay, for this case, okay, I have written here A naught is open loop voltage gain or differential gain, and the value is infinite for ideal op-amp, right? Third point, is the CMRR value is infinite. Okay, that is it's having a 0 common mode gain. Okay, what is CMRR? CMRR is common mode rejection ratio. Common mode rejection ratio. Okay, common mode rejection ratio. Okay, so basically it means that by what amount it can reject the common part which is there between the two input signals. Okay, remember, if you are having two input signals V1 and V2, and there may be some common signals, and there would be one different signal. Okay, and the task here is to amplify the difference signal and not the common signal. And there is a reason, very good reason behind that, why we would want to cancel that common part. Okay, we will come to that thing later. But remember here that we want to reject the common signal, common part that is there between the two input signals, and that capacity is given by this term CMRR. Okay, and it is infinite for an ideal op amp. Okay, and in terms of expression, it is given by this expression, that is 20 log mod of AD by mod of AC, where AD is the difference gain and AC is the common gain. Okay, that they are related to the difference signal gain and the common signal gain. Okay, and we can express output voltage, that is V out, in terms of AD and AC like this, that is equal to AD dot VD plus ACM dot PCM, where AD is the difference gain, VD is the difference. It means that this term gives us the amplification of the difference signal part, difference signal multiplied by its amplification factor. Okay, plus the common signal multiplied by its common amplification factor, right? And we want this term to be 0. We want this term to be 0 for an ideal case, so that we are only left with this term AD dot VD. Okay, and it's having an infinite open loop gain that we had just seen. Okay, and an ideal op amp also have infinite bandwidth, so it means that it will operate it can operate at any particular frequency. So it means that the op amp can operates at, can work at any frequency. Basically, this is the meaning of having an infinite bandwidth. Okay, it's having no drift, that is the performance does not change with the different with the change in parameters, temperature and other things. Okay, so it suffers no drift, and that's a good thing. Okay, and the slew rate, let's see, slew rate is the maximum rate at which the op amp output can change in volts per microsecond. Okay, that is delta V naught by delta T, where delta V naught is the change in output voltage. Okay, and delta T is that is, it is with respect to time. Okay, and this delta T is measured in microseconds, and delta V would be in volt. Okay, so it means that how fast your output can change with respect to voltage, with respect to time. Okay, so it's again a kind of you can think of it as a kind of sensitivity of the op amp. Okay, that is how sensitive your op amp is with respect to time. Okay, sensitive to what? Sensitive to time. So for what amount of smallest instance of time your output can be measured. Okay, your output can change. Okay, and so if it comes for an ideal op amp, definitely we would want a very high value for slew rate. It should be maximum, it should be infinite. Okay, but for the case of practical op amps, we want it to be a maximum value. Okay, as high as can be achieved. Okay, so this slew rate actually defines the ability of op amp to handle varying signals. Okay, then okay, we can write if V1 and V2 are the input signals, input signals, then we can write V1 as V1 plus V2 by 2 minus V2 minus V1 by 2. When you solve this, you will actually get V1. Okay, and similarly we can write V2 equals to V1 plus V2 by 2 plus V2 minus V1 by 2. Okay, when you again solve this, simplify this, you will get V2. Okay, and why it is done? Because remember, here there are two cases. One, the difference between the two signals, and the other, the common part between the two signals. Okay, where V1 plus V2 by 2 is the common part between the two signals, and V2 minus V1 is the difference part. Okay, so we can write the input signal in terms of the common mode part and the difference part like this, that is V1 is equal to VCM minus VD by 2, and similarly we can write V2 also equals to VCM plus VD by 2. Okay, so this is just another way of writing V1 and V2 in terms of common mode and the difference part. Okay, and why it is done here? Because remember, these two things are very important when you are dealing with op-amp, the common part and the difference part, and always we want to amplify the difference part. Okay, we do not want to amplify the common part. Okay, this is the basic buffer or also called as unity gain amplifier, a voltage follower circuit where the output voltage follows the input voltage. Okay, so here if okay, this is the output voltage V0, that will follow the input voltage V in, and here V0 will be equal to the input voltage. Okay, and the input impedance would be infinite and the output impedance would be 0. So basically it's a buffer which can be used wherever the need arises in a circuit, in a big circuit. Okay, so it's basically designed with 100% negative feedback. Okay, and look at here, the output signal is fed back to the input side, and that is to the negative, to the negative terminal. So it's a kind of negative feedback. Okay, and since there is the signal is completely fed back to the negative terminal without any insertion of resistance or capacitance or anything, so it's 100% negative feedback case. Okay, and we all know that buffers are used because the voltage gain for the buffer is 1. So it means that the output voltage is equal to input voltage. Actually, it is not offering us any voltage gain. So, but then what is the use of this voltage follower? The main use of a voltage follower or a buffer is in impedance matching. Okay, because look at here, the input impedance is different from the output impedance. Okay, the input impedance is infinite when you look from this side, and when you look from this side and when you calculate the output impedance, this is 0. Okay, so if there is a circuit where we want to isolate two terminals and the two terminals are having different values of impedances, and you cannot connect those two terminals directly, then it's better to insert a buffer like this, which will do the job perfectly in those cases. Okay, then let's come to this the difference amplifier circuit. So basically this is a difference amplifier that is built using op-amp. Okay, look at here, the circuit consists of two voltage sources, V1, V2. V1 connected at the negative terminal and V2 connected at the non-inverting terminal, and there are four resistances used. This is R1, this is RF1, the feedback resistance. Okay, this is R2, and this is the second feedback resistance, RF2. Okay, so the derivation we are all aware of, that how to derive the output voltage equation in the case of op-amp. So let's go through this quickly. At node A by KCL, when you apply KCL at node A, remember this is, look at here, this is node A. So when you apply KCL at node A, and we know that the input current into op-amp is assumed to be 0. Okay, so input current in this branch as well as in this branch into op-amp should be 0. So that's why I have not mentioned here. So we can very safely write that incoming current at node A, that is I1, is equal to outgoing current at node A, that is I1 dash. So I1 is equal to I1 dash, and now express this in terms of voltage and resistance. So I1 is basically appearing passing through R1. Okay, so we can write V1 minus VA, where VA is the potential of node A, divided by this R1, okay, for I1. So this becomes V1 minus VA by R1, and for I1 dash we can write VA minus V0 by RF1, VA minus V0 by RF1. Okay, and node B, again apply KCL, that is at this node B, apply KCL. Again we assume that the input current into the op amp is 0, so we are only left with two current, I2 dash and I2. So we can write by KCL that I2 dash is equal to I2. Okay, I2 dash equal to I2 here, and again express this I2 dash and I2 in terms of the voltage difference and the resistance. You will get this equation or this equation, right. Now from 18 and 19 equation number, that is this equation and this equation, okay, and we use the concept of virtual ground in the case of op amp. We know that the voltage at node A would be equal to voltage at node B, and this is what virtual ground concept says in op amp. So let's use this, that is VA equals to VB, sorry, okay, and VA equals to, you make VA equal to VB, okay, and you find the equation for VA from here and the equation for VB from this equation. Equate these two equations and you will get this one, okay. You simplify the equation, make the simplification, okay, and again use one more condition, condition that RF1 by R1 equals to RF2 by R2, that is the ratio of the feedback resistance RF1 by R1, let's take this equal to as RF2 by R2, okay, so that this becomes a common such as RF by R. So replace RF1 by R1 and RF2 by R2 by RF by R, a common equal part, a common equal value ratio. So when you do this, use this condition, and in this equation and finally you will get this equation, okay, that is V naught equal to RF by R into V2 minus V1. V naught, that is the output voltage, equal to RF by R into V2 minus V1, where V2 is the voltage applied at the non-inverting terminal and V1 is the voltage applied at the inverting terminal. Okay. So basically what does this equation says, that for this difference amplifier V naught would be amplifying this V2 minus V1, this input signal difference, by a factor of RF by R. So this becomes the amplification factor for this particular difference amplifier. Okay, and if you want to amplify this difference, then RF should be higher than the value of R. Okay, then only it will be, the ratio will be greater than 1 and the output voltage would become higher in value as compared to the difference signal. But remember that you cannot increase the value of RF by R ratio as you want, okay, as per your wish. There is some limitation when you use a practical op-amp circuit, okay, and that limitation is given by the power supply that is being supplied to this op-amp circuit. Okay, suppose V1 is, let's say 10 millivolt, V2 is, let's say 50 millivolt, okay, and 50 millivolt and 10 millivolt, so it becomes 50 minus 10, that is 40 millivolt. Okay, now you want to amplify this 40 millivolt signal, okay, and let's say the power supplies are let's say just for the case plus minus 10 voltage. Okay, so if these are the power supply values, it means that you cannot whatever value of V naught comes from this equation, it should not exceed the value given by this power supplies, which is actually fed to the input to this op-amp. Okay, if this value comes within this range, then it's fine, it's not a problem. If this value comes higher than this plus minus 10 value, suppose it comes out to be 12 voltage, which is actually higher than 10 voltage. So there is a question whether you can get a 12 voltage signal from this op-amp output when the power supplies are actually given as 10 voltage. Okay, so it will not work, in this case, and you will get a value at the output which will be equal to 10 voltage and not 12 voltage. Okay, so if you get any value that's higher than 12 volt, that's higher than 10 voltage, you can get a maximum value of plus 10 voltage at the output signal. Remember this thing. Okay, and use this thing when you are designing or when you are working with op-amp circuits. Okay, so there is a limitation. Okay, so there is a note that an ideal difference amplifier amplifier amplifies only the differential mode portion of the input voltage and eliminates the common mode operation. Because look at here, in the equation there is no term of the common mode signal, that is something like V1 plus V2 by 2 or something like similar to V1 plus V2 by 2. There is no term here, it just consists of one term, and that clearly says about the difference signal part. So this is a pure difference amplifier circuit. Okay, so you will not have any problem that will be caused by the common signals appearing at the input terminals. Okay, so that is good. And remember why we are trying to ignore the common mode signal, because of this fact that this provides immunity to noise common to both inputs. Okay, because if these are two terminals, okay, this is first terminal, this is second terminal. Okay, and we know that if we are using two supplies, two voltage sources, then there is a very good chance that they both of them would be affected by the noise, external noise. Okay, and since they are placed close to each other, the amount of noise may be equal, would be very close to each other. So similar amount of noise would affect this terminal as well as this terminal. It means that the noise part is common between this terminal, okay, this signal and this signal. Okay, so if it is eliminating that common part, it means that it is eliminating that noise also. Okay, so that common part noise gets eliminated. Okay, and it just amplifies the difference of these two signals, and that is why this difference amplifier is so important. Okay. Okay, so let's see this circuit called as instrumentation amplifier. So the application of this instrumentation amplifier would be to amplify very small magnitude signals, that is very minute signals can be amplified. Okay, and the characteristic is similar to differential amplifier. Okay, it's having a very low value of DC or offset voltage. Okay, and but the input impedance is higher than differential amplifier, so having some advantage over differential amplifier. It's generally used for sensing force, velocity, pressure and other physical parameters that are sensed by the sensors, and we know that the output of the sensors are generally very small in magnitude. Okay, and we cannot work with those small magnitude signals, so there is a need of amplification, and for amplifying those signals coming out from the sensors, generally instrumentation amplifier is used. Okay, so this is the basic DC differential amplifier, difference amplifier that we had just seen, and the gain was actually equal to RF by R1, okay, where RF is the feedback resistance, this one and this one, and R1 is the resistance connected at the input side, and these two are equal, R1 R1, okay. And now this is the circuit for different instrumentation amplifier. Look at this. How is it different from difference amplifier? This portion, the second portion, is similar to difference amplifier. So this is basically the difference amplifier portion, okay, and the first portion is actually the buffer stage, or voltage follower is actually the buffer stage, okay. So just an addition of one stage, buffer stage, to the input of difference amplifier converts it into instrumentation amplifier. Okay, so we have this instrumentation amplifier is actually using three op-amps, A1, A2, and let's name this as A3. Three op-amps are used. This is the feedback resistance RF, this is R1, this is R1, this is again feedback resistance, and at the input of this R1 and R1, two buffers are added, okay, and the input signals are provided into these buffers, V1 to this A1 buffer and V2 to this A2 buffer, okay, simple. So when you do the derivation, look at here, at this is the output of this buffer A1, and we know that the value of output value of buffer is equal to its input value. So basically, if this terminal voltage is VO1 dash, VO1 dash, this will be equal to its input voltage V1. So basically V1 is appearing here, simple. Similarly, V2 is appearing at this terminal. So in a sense, we can say that we are actually applying V1 and V2 to the difference amplifier, okay. So if so the output expression for this difference amplifier stage can be written by looking at that equation that we had just seen for difference amplifier. It was simple. The gain factor was there, RF by R1, this is RF, this is RF, this is R1 R1, multiplied by the difference of the input signals, okay. The non-inverting signal is VO2 dash and the inverting signal is VO1 dash. So it's basically VO2 dash minus VO1 dash. This should be actually VO2, okay. So there is a small mistake here, take care of this, and this should be VO1, okay. So let me write VO2 VO1 dash, and since VO2 dash is equal to V2 and VO1 dash is equal to V1, so we can write that VO actually equal to RF by R1 into V2 minus V1, okay. So it's pretty much simple, it's pretty much similar to the difference amplifier. The advantage that we have get by doing this modification that we get is it gives you higher impedance as compared to the difference amplifier, okay. And the gain is given by this ratio, only a ratio of two resistance values. So some improvement is needed over this gain value. So let's see if something can be done on this. So let's see one standard industry standard triple op-amp instrumentation amplifier, okay, and you should compare this circuit with the previous one, this one. So look at here, it is using 1 2 3, again 3 number of op-amps. It was also using 3 op-amps, okay, and RF R1 same, RF R1 same, right, V1 V2 same, just there is an addition of 1 2 3 resistances here in this branch, okay. So this node is connected to this node and there is an inclusion of 3 resistances, okay, and this is the small modification. in this industry standard triple OPAMP instrumentation amplifier. Okay. So this is the buffer stage that we had already seen. Okay, and this is the difference amplifier stage. Right. So let us okay, and this will give a higher value of CMRR. Okay, and input impedance would be again higher as compared to a simple instrumentation amplifier, and the input output voltage would be given by this term equation, R by R1 into V2 minus V1 into one more factor. So this factor has come extra here, 1 plus 2R by Rg, where R is this, R is that this R and this R is same, and Rg is also called as the gain resistance that is connected in between these two R. Okay, this is called as gain resistor and is actually provided outside the IC for the user to change its value, for varying its value. So you as a user can actually change the value of Rg, and remember this is in the denominator. So when you make it small, the gain increases. When you make it large, the gain decreases. Okay, right, but take care that you should not make this 0. When this becomes 0, there the problem comes. Okay, so it is actually used in industry and in the design of analog circuits, precision applications, sensor signal processing, and these kind of things. Now let us see the derivation part for this, for this equation for V naught output voltage, and for the derivation part for this industry standard OPAMP instrumentation amplifier, superposition theorem would be used. Superposition theorem would be used. So when we have multiple sources of voltages, we know that when we apply superposition theorem, then we take one at a time and we disable the others, and then find the value of output voltage, and then repeat the process for each individual sources, and then in the last we add all those output voltages to get the final voltage. So this would be done here. So first let's assume that V2 is equal to 0. So this is disabled first. Okay, if this is disabled, we are left with only one input voltage source. Okay, V1. So you can apply KCL. Okay, this is actually equal to no. You apply VO1. Can we write the equation for VO1, that is this particular node voltage, that is the output voltage of this A1, as 1 plus R by Rg into V1, because this is acting as a non-inverting amplifier. Look at here, the input voltage is connected at non-inverting terminal. Okay, and this is the feedback resistance. This is okay, and since this is 0, this is disabled, this is 0, so it makes this terminal 0 and this becomes actually 0, ground. So this terminal is connected to ground. Okay, and this is the feedback resistance and this is the input resistance Rg connected and in the input branch. So this becomes like behaves, this is actually a non-inverting terminal, non-inverting amplifier whose equation can be written like this. Okay. So by KCL can we write that VO1 by R plus Rg equals to minus VO2 by R minus VO2 by R. When you apply KCL at this node, we apply KCL at this node. Okay, just a minute, just a second. Okay, so okay, we apply KCL at this node. Okay, so and remember that the input current to the op amp is assumed to be 0, so this terminal will not be having any current. Similarly, this terminal will not also conduct any current. So straightforward, you can apply KCL at this node. So this becomes incoming current, let's say VO1 minus 0 by R plus RG, that is equal to 0 minus VO2 by R. So this is what is coming here. Okay. Similarly, not similarly, so also we have VO dash equals to RF by R1, VO2 minus V1. Okay, for this difference amplifier stage. Okay, because under this condition, when V2 is 0, let's assume that the output voltage is V0 dash. Okay, and this V0 dash can be written by this difference voltage difference amplifier equation, okay, that we had just seen. Okay, and put up the value of V02 and VO1 from these two equations into this equation, right? So we will get an equation for VO dash that will look like this. Okay, so take this, keep this equation. Okay, next what we will do is now we will assume that V1 is 0. So let's make this 0 and let's apply this to the input side, and in this case let's assume that V0 double dash is coming here. Now since this is made as 0, so this node will become 0 and this node will become grounded. Okay, and this does not draw any current, this does not draw any current. Okay, so look at this. Okay, what kind of amplifier is it? Is it inverting or non-inverting amplifier? This equation would be used and KCL would be applied at this node. Okay, at this node, assuming that the input current into OPAMP A1 is 0 and also the input current into OPAMP A2 is also 0. So similar thing would be done here, and when you do this, assume that V1 is equal to 0, right? So that will act as a non-inverting amplifier. Use this equation, and by applying KCL this will come, and for difference amplifier this equation is there. So put up the value of VO2 and VO1 from these two equation into this, you will get an equation for VO double dash, this one. Okay, now the final output would be the summation of VO dash and VO double dash, because we are using superposition theorem. Okay, so first condition voltage output plus second condition voltage output should be summed up to get the final value of output voltage, and after simplification you will get an equation for this V0 like this, that is RF by R1 into 1 plus 2R by RG into V2 minus V1. Okay, so V2 minus V1 and RF by R1 was there in the derivation in the equation for difference amplifier. Okay, what extra term has come here? That is this one, 1 plus 2R by RG. Okay, so the gain has increased by a factor of 1 plus 2R by RG. Remember this. Okay, as compared to difference amplifier, right? And this RG is given outside IC, for user to change the value, to vary the value. Okay, so you as a user can actually vary the value of RG to increase or decrease the value of overall gain of this instrumentation amplifier. Okay, but take care of this, that you should not make it 0 RG, then it will become a problem. Okay, so gain has improved by a factor of 1 plus 2R by RG, that's fine, and by varying RG gain can be controlled, that's also okay. RG given outside IC for varying, fine. A resistance is connected So when Rg becomes 0, that's a problem. Okay, so to solve this problem, resistance is connected in series with Rg to avoid damage caused by having Rg equal to 0. So what you do, you can fix, or when the manufacturers also can add a small value of fixed resistance in series with Rg, so that when if accidentally you make Rg equal to 0, even then in that case this would not become completely 0 in the denominator. So in that case, because Rg plus some constant value of resistance is coming here in the series part, as because they are connected in series. So when this becomes 0, then also at least you are having Rc in the denominator, and it will function properly. Okay, so this was about instrumentation amplifier, and then we will see the next topic in the next class.